Hello and good day to you. So today I'm doing a video on gradient descent. Some of this is a little bit for myself. I have found it hard using this sort of arcane little piece of maths, which really is at the heart of why neural networks work. And I never felt that I could explain it very simply or discuss it very simply. So this is me setting out to do that and make it more open to other people. Now, the idea of gradient descent is the maths that trains AI is about falling down mountains. Now, at the first instance, you might sit there and think, meh, but tell me that doesn't look like a slope. So this is the loss function for a single weight in a neural network, and the numbers are its step. So 0 is where it started, 1 first step, 2, 3 and 4, and 4 is where the error is the lowest, where the accuracy at the neural network is at its absolute peak given its inputs. Now, something to sort of take away from here is it's not just walking down the mountain, which some methods of neural network improvements might look like. It is, in this particular instance, looks more like falling down the mountain, because that first step looks like a bit of a leap of faith. And that is because of the particular method I'm using. And something interesting that it took me a long time to learn is there isn't one magic equation for how to update a neural network. There feels to me to be one magic equation for figuring out the right direction of the descent, but not for how far you should walk. And I'll move through that and get to that. But the idea here is there's two metaphors going on. One is I have a current weight of where my neural network's at the moment, and I have a inputted value into the neural network, which is the error that's being back propagated, which kind of ends up working as a calculated vector between where I am now and where I want to go to. Now, if we then think through that, most neural networks aren't just using 2 dimensions. They're not using an x and y like a map does. They might have 10 dimensions, but that's okay. You can have a vector in 10 dimensions. So that doesn't stop the metaphor of it working like a mountain. The next one is, well, we have a derivative and a activation function, but that actually makes the mountain metaphor even more true, because the derivative of your nonlinear activation function mathematically works a lot like a curve in how you move down the slope. So, having set my case out of why I'm talking about this metaphor, I'm going to then move through the maths and try and convince you that I'm not completely crazy, though I may fail. The metaphor feels clumsy, but think of it like this. There are, in a very multi-dimensional neural network, going to be plateaus and points where the AI can get stuck in training, it can get lost. There's regional optimum that might not be the true global optimum. And a lot of the complexity of training different AI is about making sure a neural network doesn't get trapped in a regional optimum and not end up in the global optimum. Then it gets more confusing because people have thrown several different algorithms, but I'm going to make the argument later that all these are different ways of working out how far you or how fast you should walk down the mountain, not for working out the direction of travel. And like most climbing teams, there's these plateaus, there's these points of pause in training a neural network. So hopefully this will convince you that there is something to this idea of it being like a walking down a mountain, and that doesn't break or change the more neurons you add or the more complexity you add. Though it only remains true on the when looking at an individual neuron. Taking the ReLU for example, it does look much more like a collapse because some values being pushed into zero are no longer taken as important to how the particular neural network calculates and does its matrix calculations. So the sigmoid takes much longer to train than the ReLU because it pushes its values in different directions, which is one of the reasons it's used as a much more modern activation function. So the maths is in front of you, and if you look at Wikipedia's description of gradient descent, it is all about following the direction or negative of the gradient, i.e. working out a direction of travel and moving it towards it. Now, I'm going to make my argument that this is some scrappy code that I'd written years ago, maybe not years ago, but a while ago. And you can see E for error. You've got the derivative of the sigmoid, and the supply is representing it's basically a list representing what the neuron's done in the last forward propagation. And then doing the back propagation, it's going backwards through its layers, which is why I say the metaphor doesn't break down regardless of how many neurons or layers, because the error is calculated anew for each layer. But you get this update, and it's proportional to the error multiplied by the derivative of the layer's outputs, and also figuring out what was put into it. So this is one of the places where the metaphor of talking about gradient descent as a travel down the mountain breaks, because unlike a normal vector, you're not just figuring out the direction based off your current position, but you do have to take into account where you're coming from. But that's because you do need to create this chain rule to pass it on to the further layers. So my metaphor breaks down a little bit, but I still want to continue with it for a while, because I feel like this is the only way to get data analyst type people thinking about neural networks and how to use them and applying them more broadly. Because I really think that a big problem with AI is it isn't very democratized at the moment. But this is where I come to say, it seems to me that it matters about finding out the right direction of travel in your multi-dimensional n phase space, or whatever you want to call it, that represents all the different ways that neuron could be weighted and put together. But having figured out a direction of travel, I'm now going to show you why the speed or the learning rate of how fast you go down the place doesn't matter so much as finding out the direction, and a little bit of the extent of how the steps is worked out by that previous piece of code, because it is already proportional. So here we go. Full learning rate 0.9, 0.8, 0.7, and you can see the neural network would still get there even with a reduced learning rate. Now that's not uncommon. Everybody knows about learning rate. People commonly use values less than 0.1 for learning rate. It's got a big deal. It's kind of a big deal because of overfitting. If we trained our values all the way to the bottom of this valley, and we got to the very lowest error in the network, we wouldn't have actually trained our neural network on the best possible minimum error on all the global data. We'd have trained our AI on the best possible output for the data you have, which is different and subtly different, and something that will throw a lot of amateur people. And it also works, and this is a bit where I'm starting to say what matters is figuring out the bearings in the multi-dimensional space. It does work if you have a learning rate of greater than 1. You can even get very lucky and find a value where it just jumps onto the right position. And even in a fully connected layer, I didn't expect this to work. I expected this to break and expected it to lose convergence with its later layers, that this sigmoid function would break down. I don't think this would work for ReLU, but it did work for sigmoid, so I found this interesting and I'm sharing it. It doesn't work if you do to negative values. So that's for 1 neuron. We're talking then about the derivatives previously. Well, if you think about it, your error is if you calculate it as a straight line, and if you were to go straight line, you should be able to get to the bottom of the plateau in 1 step. But introducing this nonlinearity and then calculating the derivatives for it does reinforce this concept of the mountain, because it is what creates that slope, and rather than the direct point-to-point travel. And so I'm going to make a claim here. Ignoring the maths, ignoring the many dimensions, gradient descent feels to me to be very much calculate the curve and follow the curve. You might disagree. I kind of felt doing this sounds like an oversimplification, and there's probably a bunch of mathematical minded people who are screaming at this screen at this point. Sorry. But it's made it make sense for me, and I hope it makes sense to somebody else, and maybe makes them interested in your networks. And I also think there's quite a nice mathematical lesson. Work out the right direction of travel, and a lot of the other complexities fall into place. What I expected to do for this video was to sit down and look at stochastic gradient descent and Newton-Raphael methods and all these other ways of doing complex methods of training a neural network. And I just found that I couldn't really explain them without really going back and understanding gradient descent in a lot more detail. So this is why this video exists. Thank you and have a good night.